Right. So where was I? So who's going to remind me? Yeah. So I already have the answers to this question already, which was KG. Which was K if B1 equals J times A minus 1. And if I know that B1 is purely imaginary, this must imply that A minus 1 and A plus 1, they must be real. Okay, so they must be real. मेरी आवाज आ रही है, right?
Yes, sir.
All right. Okay. Right. So we know that A naught is 0. We know that A plus 1 and A minus 1 are real, right? And they are conjugates, complex conjugate or conjugate symmetric, right? So, and since A minus 1 equals A plus 1 conjugate, because the signal is real, therefore the Fourier series coefficients must be conjugate symmetric, and A minus 1 and A plus 1 are real. What can I say about A1 and A plus 1? Right? If A plus 1 is real, what is the conjugate of that?
So real का तो conjugate real ही होता है, same
Real
होता है. तो
so from here I can
तो
conclude that A minus 1 equals A plus 1, right? Both of them are the same. Right, excellent, right? Now here's so the final step, which is from the last property, which was the so from property number 5, which was given was 1 upon t summation t x of t absolute squared dt. So remember this was 4, right? So let me just plug it in, and this was 4. This was equal to half, right? I just use Parseval's relationship, right? And Parseval's relationship therefore says that A minus 1 absolute squared plus A not absolute squared plus A1 absolute squared, this must be equal to half, right? But since this is 0 and A plus 1 and A minus 1 are exactly the same, what do I conclude? This implies K A1 absolute squared is equal to 1 upon 4, and which implies that A1 absolute is equal to 1 by 2, right? If a square is 1 by 4, the thing itself is 1 by 2, right? The absolute value is 1 by 2. So what can I say about A1? What can I say about A1? Right? If absolute value of A1 is half, so I don't know exactly what A1 is, but I know that's real. I mean, that's for sure. So if it's real, it would be either plus half, as Hassan suggests, or it would be minus half, right? So that's an ambiguity that I'm going to be left with always, right? So therefore, this implies that x of t is equal to A1 e raised to power j pi by 2t plus A minus 1 e raised to power minus j pi by 2t. So this is either equal to half e raised to power j pi by 2t plus half e raised to power minus j pi by 2t, or equal to minus half e raised to power j pi by 2t, or minus half e raised to power minus j pi by 2t, right? And from here we conclude that x of t could is either plus or minus cosine pi by 2t, right? Is that clear? Any questions here? No questions? Okay, so this wraps up our discussion on the properties of Fourier series. We are going to go ahead and discuss the last section within this chapter, which is, I mean, how Fourier series and LTI systems, and what is the interplay in there, right? So I'm going to start out with just trying to see, KD, if I have an LTI system, and let's say the input to that LTI system is a complex exponential, I want to see what the output of that LTI system turns out to be, right? So, so here's the section, if you will, subsection would be response of LTI systems to complex exponentials. I mean, why are we talking about this? That's I'm going to talk about just a bit. पहले थोड़ा सा analysis कर लेते हैं, right? So what is a complex exponential? Complex exponential is a signal. So complex exponential, when I say it's a complex exponential, what do I mean? So it goes back to our discussions earlier. A complex exponential is x of t is equal to e raised to power st, right? Where s is equal to sigma, some sigma plus j times omega, where sigma is the real part, right? So this is the real part of s, and omega is the imaginary part of s, right? And that makes up a complex exponential. If s equals 0, the signal is a periodic complex exponential. If s is not equal to 0, then it's either a decaying or a growing complex exponential. Okay, right? So in the real domain, it grows, a sinusoid which grows, or decays which grows, and it's similarly in the imaginary domain. Okay, so something we talked about earlier, right? So e raised to power st is something called a complex exponential, as we know, right? Okay, so the question here is the following. The question is, if I input this complex exponential to an LTI system, right, which has an impulse response h of t, what do I get, right? So let's say e raised to power st is an input to an LTI system, which has an impulse response given by h of t. What is the output? Right? Let's try to analyze that, right? So y of t, I know, is the convolution of the input and the impulse response, right? So this is minus infinity to plus infinity, just the definition of, so I would rather use this definition, h of tau and x of t minus tau d tau, right? That's just the definition of convolution. This is minus infinity to plus infinity. This is h of tau, and x of t minus tau is e raised to power s t minus tau times d tau, right? And what I then get is e raised to power st can come out of the integral because that's not a function of tau. And the integral is over tau, integral from minus infinity to plus infinity. This is h of tau, and this is e raised to power minus s tau d tau. Now, what's clearly, or what's really interesting or exciting is the following fact, that what the output now turns out to be equal to this, is of the same form as a complex exponential, except that it's just been multiplied by some number, right? So here, this thing that you see here, what is this a function of? So let me ask you this. This is a function, all right, right? So this is a function, but this is a function of what variable, right? Daniel says it's a function of tau. It's not a function of tau, Daniel. Tau is a variable that you're integrating over, right? So once you've integrated over the variable tau and plugged in the values from minus infinity to plus infinity, you get something constant, but that constant नहीं, but एक पैरामीटर रह जाएगा. कौन सा रह जाएगा? T. Mustafa says S. Excellent, right? So it's going to be a function of S, because if I change S, this value is going to change. right? So depending on what the value of S is, this value is going to change, right? So therefore, this thing is a function of S, and we say, okay, this is H of S, which is, I am pretty sure you have done in one of the other core courses that you're taking right now, right? So we say, okay, what happens is, what the output is of the form y of t equals e raised to power st times h of s, where h of s is given by this integral from minus infinity to plus infinity, h of t e raised to power minus st dt. I mean, don't worry about the fact that I've just replaced tau with t. Tau is just a variable and just replace that with t, okay? By the way, what is h of s? Right, so basically it's a Laplace transform. Even though we're not explicitly talking about what Laplace transform is right now, at the moment, we just say this is some number, right, which turns out to be a function of s. And the definition is you integrate it, the impulse response multiplied by e to the minus st, and you then integrate from minus infinity to infinity. What you're going to get is something which is a function of s, right? The interesting thing is, okay, the output, if the input is a complex exponential, the output is also a complex exponential, right? So what the interesting thing is, the output is also a complex exponential. Multiplied by some complex number, by the value h of s, right? So if the input is a complex exponential, the output also turns out to be a complex exponential. Now, in linear algebra, I'm sure you would have, just let me put this on the side here. In linear algebra, if I take a matrix A, if I multiply that by a vector x, and if it turns out that turns out to be the same vector x times some constant lambda, we say that this x is some specific, we have a specific term for this x. What term is that? Eigenvector, right? So I mean, all the doubly majors should know this as well, by the way, right? So x is known as the eigenvector of the matrix A. And somebody else other than Hassan, what is lambda known as? What is lambda known as?
Eigenvalues.
Eigenvalue for this particular x, right? Because there could be other eigenvectors for the same A, and therefore corresponding to those eigenvectors, would you have another eigenvalue? Okay, so this lambda is a function, I mean, tied up with x. Okay, so just like that, what we've noticed here is if the input to an LTI system is e raised to power st, the output is also of the form e raised to power st, except that e raised to power st is now multiplied by some constant, right? And that constant, going by the same analogy as we have with linear algebra, we say, therefore, that the complex exponential x of t equals e raised to power st is an eigen, we don't say eigenvector, but rather eigenfunction for an LTI system. With corresponding and this is called eigenvalue h of s, right? So these are the terms that we define. So this is called eigenvalue and eigenfunction. Okay, there's another color here. Eigenfunction, e raised by st is an eigenfunction, and h of s for that particular s is called the eigenvalue. Right? Any questions here before I talk about SK? What is the application here? Right. Now, so from here, what we can say is, um, So what is the response of an LTI system to a periodic signal? Right. So here's one of the interesting bits here. If there's an LTI system which has an impulse response equal to h of t, and I say here, let the input to this LTI system be x of t, which is periodic and for which the Fourier series decomposition exists. So therefore, x of t can be written as a summation of these complex exponentials, ak times e raised by j k omega naught j k omega naught t. What is y of t? That's the question we want to answer, right? Now, one of the ways you can say is, let's just do convolution, right? So if, for example, it's a square wave, which is input to LTI, let me just take the square wave and integrate that from minus infinity to infinity and do that convolution, right? But it turns out it's a much easier problem. If you have the Fourier series decomposition, you can just use the result that I just derived above and linearity of the LTI system to come up with the result directly, right? How? How is the question? So any ideas? What would be the output? So the input is summation this ak times e raised by jk omega naught t, right? So what would be the output? So if I know, so let me start with this. If e raised by j k omega naught t is the input to an LTI system, right? So this is LTI. Right. Okay, so let me baby steps, Hassan. Let me start with baby steps. You're many steps ahead of me. Right. So what would y of t be? So let me ask somebody else. Okay. If e raised by jk omega naught t is the input. Okay, Daniel, good. Daniel, can you unmute yourself and so e raised by jk omega naught t, isn't that a complex exponential as we've seen? It is a complex exponential. The only difference from और क्या है कि वहां पे s था, यहाँ पे we don't have s anymore, right? In fact, the sigma, which is the real part of in the exponential, is 0, and there's only an imaginary part, which is fine. Okay. So what would be the output, Daniel?
Sir, am I audible?
Yes, you are.
Sir, ये e raised power jk omega t
Right,
multiplied
by
h of s.
h of s, and s equals jk omega naught t, right? So the key idea is that s is actually equal to jk omega naught t, and all I've done is the result I derived above, I just replace s with jk omega naught t, and I get this result. Okay. So excellent, Daniel. Right. So somebody else, if I multiply the input with AK, what happens at the output? Umar Abdul Jalil.
It's also multiplied by two.
Umar, please.
It's also multiplied by two.
Okay. So if I hear you correctly, you're saying that you just multiply with AK, right? That's because of linearity. Okay. What if there's a summation at the input?
Of the output as well.
The output with summation. That's it. And here's the output. There you go. So if x of t is the input, which is a summation of complex exponentials, y of t takes this form, right? So I conclude the y of t, therefore, let me write this clearly. This is summation k going from minus infinity to plus infinity, ak times h of j k omega naught times e raised by j k omega naught t. Okay. So the output is of this form. If the input is a complex is a periodic signal, which is the input, the output is of this form. What can I say about this output? Can I say is this periodic or not? Yeah. Can I say something about the periodicity of this output? कौन बताएगा मुझे? Somebody who's not spoken yet, so I can jot down your name. Asan, who has not spoken yet. I mean, if there are people sitting besides Usman who have not spoken yet, they could identify themselves and speak up.
Yes, sir. वो मसला ही था.
Other than Masna.
Sir, no one.
चले और नहीं है इसका मतलब कोई. और सारे मेरे ख्याल में सर्किट्स पढ़े हैं, right? Right, Asan, or Usman, why don't you give it a shot? So the question is, can I say something about the periodicity of the signal y of t?
So I guess it is periodic with a period 2 pi over omega naught.
Okay, good. Why do you say that?
Sir, because I guess k की value infinity से minus a positive है.
Okay, good. Hassan, you said periodic as well. Hassan Shabir.
Yes, sir.
Would you like to elaborate on why your answer is KG is periodic?
Sir, because of the Fourier series decomposition,
Good.
the signals have a period of 2 pi over omega naught.
Excellent. Right. So you're exactly right. And so if you could be a bit more confident in your answer, you're perfect answer, right? Ibrahim.
So sir, मैं कह रहा था कि h of jk omega naught is a constant, तो
Yeah.
उससे हम multiply करेंगे तो फर्क नहीं पड़ना चाहिए वैसे.
Right.
Periodicity.
Excellent. Zabardast. Right. So yeah, see here. I mean, this thing here is not a function of time. It's just a function of k. Right. And therefore, these are I can say these are the Fourier series coefficients. And let me call them just bk. Right. So essentially, what you're getting is summation bk times e by jk omega naught t, which is just a synthesis or the Fourier series decomposition of y of t. And from here, I can conclude that y of t must also be periodic, and that periodicity still is with the period of capital T, right? So the period stays the same. It's not the Fourier series coefficients that are changed. And how are they changed? They are changed, as somebody said, depending on what h is, Daniel. So that's excellent. The periodicity does not change. The period does not change as a function of h. However, the Fourier series coefficients, whether they're smaller than earlier or whether they are bigger than earlier, depends on what h is or depends on what the LTI system is, right? So the output indeed is depends on what the LTI system is or what the impulse response of the system is, but the shape of it, right? But the periodic properties or the periodicity is still there and the period stays the same as well. Okay, so that's a conclusion. And we've done this all without convolution, by the way. I mean, we've not really done convolution anymore, right? I just plugged in that result of eigenvalues, eigenfunctions, and derived this result. Okay. Any questions about this before I talk about one interesting application? Right. Now, given this fact that y of t is actually equal to a summation where this ak is multiplied by h of jk omega naught, I mean, this opens up design problems or design room for design, right? Where we say, if there's a particular kind of an input, and from that particular type of an input, we want a specific type of an output. The question is, can we design the LTI system in such a fashion, which lets us get the desired output, right? So that's the question, and that's a design question, right? Now, in order to frame this in a real world sort of an example, let's do this. This is application and put this under the framework of what many of you may have at your homes. And this is DC to AC conversion. So I may have a homework related to this as well, a design problem associated with this, but let me just say something about this. So DC to AC conversion. Right. Now, how many of you have a UPS at home? A UPS, an uninterrupted power supply, right? So I mean, most of the people in today's time do, right? So किसका काम करता है? Any ideas? किसने हाथ खड़ा किया था? Daniel, right? So how do you think it works?
Sir, पता नहीं sir.
पता नहीं. सोचा कभी?
नहीं sir.
So Asad,
नहीं sir.
you have an idea of how it works?
सर वो जो वापडा से अल्टरनेटिव करंट आ रहा होता है उसको पहले डीसी में कन्वर्ट करता है, उसके बाद
Good.
उसको एक सिंपल बैटरी में स्टोर कर देता है,
Yeah.
फिर जब चाहिए होता है तो उस बैटरी से यूज करके दे देता है.
Good, right? So you're getting power from the mains, right? And that voltage there is alternating, right? So that's the sinusoid. I mean, the AC voltage that you get is nothing but a sinusoid, by the way, of 50 hertz, right? That is used to charge a battery, right? And that battery, once it's charged, it provides you with a DC voltage, right? And that DC stays constant, right? I mean, DC ka matlab direct current is just stays constant, it does not alternate, right? But your equipment or your appliances, most of the appliances work at AC. So in order for you to run those appliances from the UPS, you would need to convert that DC voltage to an AC alternating value, alternating current. So क्या करते हैं? How do you do that? There are multiple steps for doing it, right? So the first step is it has a switch inside, right, which alternates, right? What it does is it keeps on changing the polarity of the voltage. So typically the voltage is plus 12 volts, right? So it keeps on switching, right? So it plus 12 volts or so I'm going with my example here, plus 12 volts or zero, plus 12 volts or zero, plus 12 volts or zero, right? It switches with a certain frequency, right? And typically, I mean, there could be many designs. One possibility is the following, right? Okay, you have a switching circuit, which gives you this output, a square wave. And typically it switches at a frequency of 50 hertz. So if this is zero, this is 1 upon 50, right? So this is, remember, this is time t. This is 1 upon 50, and it's a duty cycle of 50%, and therefore this is 1 upon 100. So this is 1 upon 100, right? So 50% of the time it's on, 50% of the time it's off, right? That's it. That is what is meant by a duty cycle of 50%. ठीक है? अब वैसे ज्यादातर जो होते हैं ना वो चले आप वो नीचे की तरफ लेके जाते हैं, negatives में भी लेके जाते हैं, right? Now, but what you run the system at or the appliances at is a sinusoid, right? I mean, it has to have a sinusoidal waveform, right? How do you get a sinusoid out of it? Now, if I do some just apply the analysis that we've done earlier, right? So we say this can be represented in this form, this square wave. We've done that, right? Where AK is, and just applying the result directly. AK equals half, and it's sine pi k by 2 divided by k pi. This is when k is equal to 0, and this is when k is not equal to 0. And I'm assuming for simplicity, the maximum value it takes is 1 volts, right? If it's not 1 volts, it's 12 volts, so you just multiply everything by 12, right? Now, how do you want to get a sinusoid out of it? How could you get sinusoid out of it? Here's how. If I just feed this x of t into an LTI system, which has some impulse response h of t, and that's open for design. I know that the output that I'm going to get, which is y of t, is going to be equal to summation k going from minus infinity to plus infinity, a sub k is e raised to h times e raised by j k omega naught times e raised by j k omega naught t, right? Can I extract a sinusoid out of it? Do something with h. Or in other words, what values do you think h, this capital H, should take? Or what? How do I play around with them so that the output that I get is in fact a sinusoid? क्या ख्याल है? Any ideas? So maybe I'll leave this off as something for you to think about, right? So this is going to be a part of the complex engineering problem, right? So can this be played with? So that y of t turns out to be equal to some constant times cosine omega naught t. In other words, can I extract a cosine or a sine out of this square wave by playing with this h? Okay. I will stop here and stop recording.